Prime factorization is the next step after knowing which numbers are prime, which numbers are composite. You discovered in class that every single composite number is a product of primes, which means that every single composite number is made up a set of prime numbers that you can multiply and end up with the composite again. The product of primes is the prime factorization of that number. So once you figure out what prime numbers make up that composite number, you call it the prime factorization. Example is 12. The numbers I can multiply together that make 12 are 2 and 2 and 3. Now the reason we don't call 4 and 3 the prime factorization of 12 is because 4 isn't a prime number, but 2 and 2 make 4. Prime factorization can be done in two different ways, using two different methods. You can use repeated division, or you can use what's called a factor tree. 104. In order to find the prime factorization, you need to start with a prime number. First rule that I want to remind you of is that if the number is an even number, then 2 is a factor. And because 104 is even, then I know I can divide it by 2. It may be something I can do mentally. It may be something I have to go over and do 104 divided by 2 and figure out the other factor. I happen to know that the other factor is 52. Now, this is just division upside down. You can still do it right side up and stack it. I just don't have enough room. So 104 divided by 52 is 2. 52 is not prime because look, it's still even. So I'm going to divide it again by 2. And 2 into 52 is 26. And 26 is still even, which means I can divide it again by 2. And 13 is prime. And when you get to 1, you're done. So the prime factorization of 104 would be 2 times 2 times 2 times 13, and would be written like this. Now, let's try it again with a factor tree. And the cool thing about a factor tree is that you don't necessarily have to start with a prime number. Maybe I know that 26 times 4 is 104. So I'm going to start with the 26 and the 4. Now, neither one of these are prime, which means that both of these still need to have more factors. So what makes 26? Well, 26 is made with a 13 and a 2. And 4 is made with a 2 and a 2. Now, all of these numbers are prime, so we would circle them. And you can see how this looks like a tree. And our prime factorization is the set of circled numbers. So this one would be 13 times 2 times 2 times 2. Let's try 18 using repeated division. Because 18 is even, I know it can be divided by 2. And 2 into 18 is 9. 9 can be divided by 3. And 3 is prime. And when you get to 1, you're done. So the prime factorization is the set of numbers on the outside. 2 times 3 times 3. If I wanted to use a factor tree instead of repeated division, perhaps I would choose to use 3 and 6. 6 can then be broken again to 2 and 3. 3 is already prime. 1s never show up in our factor trees. We just circle each time we get to a prime number. So 3 and 2 and 3 are the numbers that I circled. Now, please remember that the commutative property of multiplication says you can put them in any order. So you can see that this red prime factorization is the same for 104, and these are the same for 18. Let's look at some more examples. Prime factors can be used in any order, and the prime factorization will stay the same. So if you're solving these and doing the prime factorization with me, if you don't pick the same factors to start with, it's not a problem, because we're going to end up with the same answer. On these, I'm going to use the tree. 45. I'm thinking of to myself, what factors do I know go into 45? What is a multiplication problem that makes 45? And the first one that comes to my mind is 9 times 5. Again, you could have thought of 3 times 15 and you would have been correct. 5 is prime, so it's circled and done. 9 is made of 3 and 3. 3 is prime, so my prime factorization is 3 times 3 times 5. 99. The numbers that come to mind for 99 are 9 times 11. 11 is prime, 9 is not. But 3's are. 3 times 3 times 11. 46. I know it's even, so that means that 2 would go here. And I know that 46 divided by 2 is 23. 2 is prime. And I'm sitting here trying to figure out if 23 is prime, and I'm remembering the activity we did in class. And so I'm going through those 4 prime factors to see if 23 was eliminated. It's not going to be eliminated by 2 because it's not even. To figure out if it's going to be eliminated by 3, you could use the sum of the digits. 3 plus 2 is 5. 5 is not divisible by 3. That means 23 is not divisible by 3. The rule for 5 is that it has to end in 5 or 0. And this does not end in 5 or 0, cannot be divided by 5. My last one was 7. And when I say my 7s, 7, 14, 21, 28, 23 is not there. 2, 3, 5, and 7. If you're not eliminated by that and you're less than 100, then you are on the prime list. So the prime factorization of 46 is 2 times 23. This asks you to complete the prime factorization of these numbers. If you'll notice, each of them have a variable, which means 2 things. You could come over here and do the prime factorization of 20 and figure out that you should have a 2 and a 2 and a 5, which means that the missing number here is 2, so n equals 2. The other thing you could do is figure out how much more you need and see if that's prime. 2 to the 3rd power is 8, and 8 times n is 24. 8 times 3 is 24, so n equals 3. This one I could combine because the commutative property says that I could change the order to simplify the expression. So what if I did 2 times 5 times n? Well, this would simplify to 10 times n, and 10 times n equals 30, so n must equal 3. So yes, you can do the prime factorization, or you can use the commutative property to solve for n. Let's look at this one. A number f is a prime factor of both 15 and 40. What is f? So what prime number would I use in both 15 and 40? Well, the prime factorization of 15 would be 3 and 5. And the prime factorization of 40 would be 2 and 2 and 2 and 5, which means the only number that is prime and common is 5. So f equals 5. Prime factorization is most often written in exponent form. So these are the prime factorizations of the numbers that we have already factored today. You can go back in your notes and rewrite these in exponent form, which simply means instead of writing 2 times 2 times 2, we would write 2 to the third power, which is, 13 doesn't have another 13. There's no repeated multiplication. So 2 to the third power times 13 is the same thing as 2 times 2 times 2 times 13. In order to figure out where to find this in your journal, you can do the math. 2 times 2 is 4, and 4 times 2 is 8, and 8 times 13 is 104. So back at the very first page, we did the prime factorization of 104. 2 times 3 times 3 could be written as 2 to the first power, which we typically don't write, times 3 to the second power. And what number does this go with? Well, 3 to the second power is 9, and 9 times 2 is 18. 3 times 3 times 5, there are 2 3's, so we write it as 3 to the second power times 5. And 9 times 5 is 45. This number, 3 to the second power times 11, 9 times 11 is 99. And then finally 2 times 23, it is written in exponential form already because there's not any repeated factors. So 2 times 23, and sometimes we're tempted to call it exponent form, so you could put a 1 there, but we know that the 1 isn't necessary because anything to the first power is itself. So most commonly you'll see that written as 2 times 23, which is the prime factorization of 46.